Modern cloud computing is built on an uncomfortable compromise. You provide the data, but someone else provides the physical machines. Three groups share infrastructure: artifact owners deploying models, compute providers offering execution, and end users submitting queries. Beneath the control plane, workloads run on shared operating systems and hypervisors. Consequently, anyone with hypervisor access or root privileges can read plain text data directly from memory. Standard security practices like encryption at rest and in transit secure data while it sits on a disk or moves across a network. But these practices leave a fundamental structural gap. To actually process data, the CPU needs it in clear text. Workloads, user queries, and proprietary intellectual property all reside in RAM completely unencrypted, readable by anyone with sufficient host access. This architecture shifts confidentiality onto legal contracts and audits, as the systems themselves lack the hardware mechanisms required to mathematically enforce these boundaries. This maps a standard Kubernetes deployment, where the control plane holds absolute scheduling authority. Because of this, a compromised control plane can schedule a malicious sidecar next to a target pod, intercepting traffic or reading secrets from shared environments. In the lower half of this diagram, the C8s architecture addresses this risk by treating the control plane as a potentially hostile entity. It draws a strict cryptographic trust boundary around the compute nodes and ingress points. Network infrastructure, storage backends, and the entire Kubernetes API server are left completely outside this perimeter. The control plane is demoted to pure orchestration. It can request that workloads be scheduled, but it has no authority to observe data or dictate trust policies within the boundary. Removing the control plane's visibility into the workload allows the system to enforce confidentiality through hardware-rooted cryptography. The underlying hardware mechanism responsible for enforcing this strict physical boundary is a Trusted Execution Environment, or TEE. Within a TEE, the CPU's secure processor encrypts memory pages using hardware-level keys the hypervisor never possesses. As software loads, the hardware generates a cryptographic measurement, a hash digest covering firmware, kernel, and user space. This is attestation. C8s operationalizes these hardware properties through a repeatable sequence. It begins by encrypting the runtime and measuring the code at launch, then binds a hardware identity to that measurement to verify connections and secure all egress traffic. Because the hardware computes the hash digest before the guest operating system even begins execution, any substitution of a malicious binary instantly changes the measurement. Instead of reading a compliance report to guess if a server is secure, external verifiers check this hardware-signed report to prove exactly what code is running. A component's identity becomes a mathematical proof derived directly from its hardware environment and the integrity of its code. Since the Kubernetes API server is outside the trust boundary, it cannot be used to issue the certificates required for secure internal communication. This schematic details the certificate distribution service, the new attested root of trust. A booting pod submits its hardware attestation to the CDS for appraisal. The CDS verifies the signature and code measurement before issuing a mutual TLS certificate. This sequence diagram maps how we bootstrap trust in the CDS. During initial setup, a human operator requests evidence from the CDS and verifies the launch digest. Once verified, the operator signs and uploads the initial policy allow list. This human verification step is required exactly once. After that single bootstrap event, all subsequent pods are appraised autonomously by the hardware cryptography. Consider a scenario where a compromised Kubernetes scheduler attempts to stealthily launch a malicious sidecar container next to a sensitive workload. C8s blocks this using an NRI hook, intercepting every container creation event. The hook compares the image digest against a CDS-signed allow list. Rejection happens at the node level. The control plane can demand it repeatedly. The node simply refuses. Compute security solves only half the problem. Because the cluster operator controls the container network interface, network infrastructure cannot be attested. C8s blindfolds the network with a remote attestation TLS mesh, encrypting all intra-cluster pod-to-pod traffic end-to-end. Because valid certificates are exclusively issued by the CDS to workloads that pass hardware attestation, an unauthorized container injected onto the network lacks the cryptographic identity to decrypt the traffic or participate in the mesh. A hijacked control plane can refuse to schedule pods, causing a denial of service, but it lacks the keys to observe, modify, or steal the data. We see how these layers interact by tracking the deployment of a highly sensitive asset, like proprietary AI model weights, into a compute cluster. This diagram captures the pod submitting its attestation report to the CDS, which evaluates 3 conditions: genuine hardware, authorized workload digest, and permitted per-key policy. Upon approval, ciphertext model weights are pulled from untrusted storage and decrypted exclusively within the pod's hardware-encrypted memory. Proprietary weights never touch the Kubernetes API server, are never exposed to the host operating system, and never sit on a physical disk in plain text. These models demonstrate boundary plasticity. In a node-level deployment, the entire worker node boots as a confidential VM, allowing multiple pods to share hardware-isolated memory. In a pod-level deployment, each individual pod boots inside its own dedicated confidential VM for strict hardware-enforced isolation. This schematic compares GPU attachment dictated by NVIDIA's confidential computing mode. Node-level configurations allow efficient GPU time slicing across pods. Because the protected state binds to a single guest, pod-level configurations require assigning a dedicated entire GPU to each individual pod. Cloud architects deploying AI inference and secure data pipelines can optimize for either resource density or strict hardware isolation without rewriting their application logic. By neutralizing the control plane and anchoring identity in silicon, C8s makes the confidentiality of Kubernetes workloads cryptographically provable to any independent third party.